Have you ever looked up at a solar panel glinting in the sun and wondered, how on earth is that made? It looks like a simple sheet of dark glass, but it's actually a marvel of modern engineering. Today, we're going on a journey from a handful of sand to the powerful panels that are changing our world. Let's pull back the curtain and uncover the secrets behind solar technology. It all starts with something incredibly common: sand. But not just any sand. We need quartz sand, which is rich in silicon dioxide. This is the raw material for creating polysilicon, the heart of every solar cell. The sand is first purified and then heated in an arc furnace at scorching temperatures, over 2,000 degrees Celsius. This intense heat melts the sand and removes the oxygen, leaving us with metallurgical-grade silicon, which is about 98% pure. But for solar panels, 98% isn't nearly pure enough. We need to aim for 99's purity, or 99.9999999% pure silicon. It sounds extreme, but this level of purity is crucial for the panel's efficiency. To reach this incredible purity, the silicon goes through a complex chemical purification process, often using the Siemens process. The silicon is reacted with hydrogen chloride to form a gas called trichlorosilane. This gas is then distilled multiple times to separate it from impurities. Finally, the ultra-pure trichlorosilane gas is passed over heated silicon rods. The silicon deposits onto these rods, growing into large, high-purity polysilicon ingots. These ingots are the foundation of our solar cells. They look like large, gray, crystalline cylinders or blocks. It's amazing to think that this dull gray material started as simple beach sand, now transformed into one of the purest materials on Earth. Once we have our ultra-pure silicon ingots, the next step is to slice them into paper-thin wafers. This is a delicate and precise process. The ingots are mounted and cut using extremely thin diamond-coated wires. These wires move back and forth, slicing the entire ingot into hundreds of wafers simultaneously. Each wafer is less than a millimeter thick, incredibly fragile, and needs to be handled with extreme care. After cutting, the wafers are cleaned and polished to remove any saw marks and surface damage. This creates a perfectly smooth, uniform surface, ready for the next stage of its transformation into a solar cell. Each one of these thin discs is a potential powerhouse. Now, we get to the real magic: turning a plain silicon wafer into a functional solar cell. This happens through a process called doping, to create an electric field, which is what forces electrons to move and generate a current. We need to create two different types of silicon within the wafer. The majority of the wafer is doped with an element like boron, which has one less electron than silicon. This creates a p-type or positive-type silicon layer. Then, the top surface of the wafer is doped with an element like phosphorus, which has one more electron than silicon. This creates an n-type or negative-type layer. The boundary between these two layers is called the pion junction. This junction is the active region of the solar cell. When sunlight, which is made of photons, strikes the cell, it knocks electrons loose from the silicon atoms. The built-in electric field at the pion junction then sweeps these free electrons toward the n-type layer, creating an electric current. It's a beautifully simple yet powerful principle of physics happening on a microscopic level. To optimize this process, an anti-reflective coating, usually silicon nitride, is applied to the surface. This thin blue film is what gives solar cells their characteristic dark blue color and helps them absorb as much sunlight as possible. With the pion junction created, we need a way to collect the electricity. This is where the metal contacts come in. A grid of very fine metallic lines, typically made of silver paste, is screen printed onto the front surface of the cell. These are the grid lines you can see on any solar panel. They need to be thin enough to not block too much sunlight, but thick enough to conduct the electricity efficiently. A full metal coating, usually aluminum, is applied to the back surface of the cell. These front and back contacts are then heated in a furnace to ensure they make good electrical connections with the silicon. And just like that, we have a complete solar cell, ready to convert sunlight into electricity. But a single solar cell doesn't produce much power on its own. To create a useful amount of electricity, we need to connect many cells together. Typically, 60 or 72 cells are laid out in a grid and soldered together in series using metal ribbons. This string of cells is then carefully placed on a sheet of tempered glass, which will be the front of the panel. On top of the cells, a layer of encapsulant material, usually a polymer called EVA, is added. Another layer of EVA and a protective backsheet, often made of a durable polymer like Tedlar, are placed behind the cells. This whole stack glass, EVA, cells, EVA, and backsheet forms the solar panel sandwich. The next step is lamination. The assembled sandwich is placed inside a laminator, which is essentially a large vacuum oven. The machine removes all the air from between the layers and then heats up, causing the EVA encapsulant to melt and flow around the cells. As it cools, the EVA solidifies, sealing the cells in a moisture-proof, durable package. This process is vital for protecting the delicate solar cells from the elements rain, hail, wind, and temperature changes for decades to come. The lamination process ensures the panel will be robust and reliable for 25 years or more out in the field. Finally, the laminated panel is fitted with an aluminum frame. This frame adds rigidity and strength, making it easier to handle, transport, and install. It also provides a way to mount the panel onto a racking system. A junction box is attached to the back of the panel. This is a small, weatherproof enclosure that houses the electrical wiring and bypass diodes. The diodes are a crucial safety feature that ensures the panel continues to produce power, even if a part of it is shaded or dirty. After the frame and junction box are attached, every single panel undergoes a series of rigorous quality control tests. These tests include a flash test, where the panel is exposed to a powerful burst of light that simulates perfect sunlight conditions. This measures its actual power output and electrical characteristics to ensure it meets its specified rating. Panels are also tested for their durability against impacts, moisture, and extreme temperatures. Only the panels that pass every single test are approved, packaged, and shipped out to be installed on rooftops and in solar farms around the globe. From a grain of sand to a high-tech powerhouse, the journey of a solar panel is a testament to human ingenuity. So, the next time you see a solar panel, you'll know the incredible story behind it. It's a story of purification, precision engineering, and advanced physics, all working together to harness the power of the sun. It's a technology that's not just powering our homes, but also powering a cleaner, more sustainable future for all of us. I hope you found this journey as fascinating as I do. If you enjoyed this video and want to learn more about the amazing technologies shaping our world, make sure to hit that like button and subscribe to the channel. Thanks for watching, and I'll see you in the next video.